Hello, this is video 75. I'm going to be going over some additional questions related to Archimedes' principle. Let's take a look. This first question asks about the buoyant force on three different blocks. We just did a problem that was very similar in a previous video where we had some blocks in some liquid and the blocks were all the same size. And we said if they're all the same size, it doesn't matter where they are in your liquid, they're all going to have the buoyant force. And this was because Archimedes' principle told us that the buoyant force equals rho fluid v fluid g, where rho fluid is the density of the liquid, v fluid is the amount, the volume of the liquid that is displaced by the object, so how much liquid is pushed out of the way by the object being there, and then g, the acceleration due to gravity. So we said that the amount of buoyant force on an object is really going to be affected by the size of that object. The bigger the object, the more buoyant force. So in this case, we have three different objects of different densities. It says that uranium is more dense than lead, which is more dense than aluminum. The reason we are given this information is because this will give us some idea of the size, because the mass of each one is the same, it's 1 kilogram. So does that mean that they're all the same size if they have the same mass? No, it doesn't, because you have different densities. Remember, density is mass over volume. This means that volume equals mass over density. So the bigger the density, the smaller the volume, right? Because it's more condensed, it's going to take up less volume for the same mass. So if uranium is the most dense, that means uranium is going to be the smallest, and then lead, and then aluminum. And I'm not drawing these to size. This is uranium, this is lead, and then this is aluminum. So can you see that aluminum is the one that would have the greatest buoyant force because it's the biggest. Let's take a look at the next example. The buoyant force on a milk carton. What is the buoyant force on a 1 liter container of milk placed in water so that it is fully submerged? So we just have this milk carton, for some reason, submerged in water. How much buoyant force is there? So this example is just so that we get used to using the definition of buoyant force. Because we've been doing a lot of conceptual questions, but how about can we plug in some numbers? Buoyant force is the density of the liquid. Now, it's not the density of milk, it's the density of the liquid in which that object is. So the density of water. So we'll go ahead and write down our givens. Density of the water is 1,000 kilograms per meter cubed. And then we need to know how much volume does the milk carton push out of the way? How much fluid is displaced? That's what VFL stands for. Well, if it's 1 liter carton of milk, it's going to displace 1 liter of water. So when an object is completely submerged, VFL is going to equal V of the object, right? When completely submerged. I'll write that down. I think this comes up a little bit later, but it's nice to have it written down already. When completely submerged. Okay, so we are given that it's 1 liter, and we are given the conversion that it's equal to 1,000 centimeters cubed. However, that's not the standard unit. We need to have this in meters cubed so that it's going to have the same units as the meters cubed here in the density. So we're going to do our conversion. We know that we have 100 centimeters in 1 meter, but when we cube the unit, we cube the prefix. So we end up doing 1,000 divided by 100 cubed. And this is going to give us 1 times 10 to the negative 3 meters cubed. And now we're ready to plug in our numbers. The buoyant force on this milk carton is going to be 1,000 times 1 over 1,000, that's what 1 times 10 to negative 3 is, times g, which is 9.8. So our buoyant force will be 9.8 newtons. So this was just an exercise in being able to plug in the numbers to actually get a number for that buoyant force. Let's take a look at this question. This is one of my favorite questions of all time. It says, a cup is filled to the brim with water and a floating ice cube. When the ice melts, which of the following occurs? Does the water overflow the cup? Does the water level decrease? Or does the water level remain the same? So how do we approach this? The first thing to realize is that when the ice melts, you know that it's going to get smaller. You know that when water freezes, it expands. So when ice melts, it contracts. So what we're really trying to figure out is when the ice melts, how much room does it take up? Does it take up the same amount of room that was pushed out of the way? Right? Before the ice cube was put into this container, let's say that the water level was up to here. And then when the ice cube was placed in the water, then this amount of ice here pushed some water out of the way, and so the water level rose up to here. So what we're trying to figure out is when the ice melts, does the water, the melted ice, take up the same amount of room as right here of the water that was pushed out of the way? If it does, if the melted ice takes up this amount of room, then the water level is not going to change. And that's actually what happens, that when the ice melts, it's going to take up this exact same amount of room, and the water level is not going to change. Now, how do we know this? So the way that we know this is because when the ice cube is floating, there are two forces on it. There's the buoyant force and there's the weight. And those forces must balance each other because the object is floating in equilibrium. So we know that the buoyant force equals the weight of the object. We also know from Archimedes' principle that the buoyant force equals the weight of the fluid displaced, the weight of the liquid that was pushed out of the way. There was this much liquid pushed out of the way. So can you see that if the two are equal to each other, that means the weight of the object, the weight of the ice, is equal to the weight of the fluid displaced, to the weight of this liquid. So that means that when it melts, it's going to become this liquid and must take up that exact same amount of room. The water level will remain the same.